Hi, my name is Taizeng Yan, student ID 03598080, February intake 2024. Today I'll be presenting an engineering math video on thermal transfer in cooling of electronic components. To start off, how does an electric component release heat with heat sink? So there's two main components, a base and fin of a heat sink. The base is actually the one that makes contact with the electronic component, which is known as conduction, and the fins is the one that dissipates heat into the environment, known as convection. So conduction, we use Faraday's law, where the heat flux represented by Q is equals to the thermal conductivity, surface area, and temperature gradient. For convection, we use Newton's law of cooling, where it states that the rate of change of temperature with respect to time, which is represented by T prime, should be proportional to the difference of temperature and its surrounding. It's kind of based on common sense, where the heat generally moves from hot to cold, and if the temperature are further apart, the rate of change is higher, and if the temperature is closer together, the rate of change is lower. Zooming in, for conduction, we look at this diagram, which states that no heat will flow along its isotherms. The isotherms is actually the lines of constant temperature in a two-dimensional space, or surface of constant temperature in a three-dimensional space. So in a isotropic materials, heat must always flow perpendicular to the isotherms, so never touching the lines, due to the heat flux vector not being aligned with the isotherms. If we label a single point on the isotherms as n, and we can rearrange Faraday's formula to give us heat flux in a single direction. So by substituting 0 into the change of x and a del operator into the formula, we can get heat flux equals to negative k delta T. For convection, we can use Newton's law of cooling and apply separable differential by throwing dt over the other side and integrating both sides, giving us e and its exponent, giving us exponential and its constant c. So applying the formula into a modeling question, where the thickness of the heatsink is 0.5 and a starting temperature of 85 and with another side of the plate as 40 Celsius, given the K as 205. So assuming that the heatsink is in a steady state condition, we can assume that d square T and dx square is equal to 0, and with that integrating its temperature gradient gives us C1x plus C2. Its temperature gradient is actually the one in the bracket. So its starting position at 85 gives us C2 as 85, and its ending position, which is 0.5 centimeters away converted to meter, is 40, giving us a C1 of negative 9,000. And then we just put it right into the origin formula, giving us its temperature distribution. Lastly, if the fin starts at 60 Celsius and the surrounding air is 25 Celsius, where its K is 0.04, find the temperature after 5 seconds. So we take the formula we differentiated with the separable differential, then we take its starting position, which is 60 Celsius, and we get its constant of 35, and substituting back into the original equation, we get this formula, which is easily found, which we can easily find the temperature after 5 seconds as approximately 53.7 Celsius.